Jai Hind everyone. Myself Dr. Sharma from Ajay Kumar Garg Engineering College. My subject is Engineering Physics and code is KS101T, and the topic which I am taking, which I have started, that is Relativistic Mechanics, and I have already discussed about frame of references, about both inertial and non-inertial frames. Then we have discussed about ether frame of reference. Then we have discussed about that famous Michelson-Morley experiment. We have discussed about the experimental setup of Michelson-Morley experiment, which is your Michelson interferometer. Then the working process means experiment was performed in 3 steps. So we have discussed all those 3 steps. Then the expected result and what was the actual result they got from Michelson-Morley experiment. The expected result was a shift of 0.4, but they got a 0 shift in the fringes. So it means Michelson and Morley experiment that failed to prove the existence of ether medium, that failed to find out any relative motion between earth and ether. After that, some explanations were given for that negative result. We have discussed the 3 famous explanations for that negative result. One was ether drag hypothesis, one was length contraction concept, and the third one, which was universally accepted, that is known as constancy of speed of light. And a very important conclusion from that Michelson-Morley or that failure of Michelson-Morley experiment, that there is nothing like that we cannot describe the motion of any object with respect to ether. If you want to describe the motion of any object, you can always describe with respect to a material object. So that was the beginning of your special theory of relativity, and special theory of relativity that started with the Einstein postulates of special theory of relativity. We have already discussed the 2 famous postulates of special theory of relativity. One is law of equivalence, according to which all the laws of physics are equally applicable in all inertial frames. Second one, speed of light is constant in all inertial frames. So next we have started this Lorentz transformation equations. Rather, we have derived all the 4 equations. And how we derived those equations? We have taken 2 inertial frames, S and S dash. S is at rest and S dash is moving, and it is moving with the constant velocity with respect to V, which is comparable to C. So then same event that was described with the help of both the observers or both the frames. For the stationary observer, the x, y, z and t were the coordinates, and for the moving observer, x dash, y dash, z dash and t dash are the coordinates. So Lorentz, he tried to correlate the coordinate along x-axis, that is x with x dash, y with y dash, z with z dash and t with t dash. So for that, he proposed that the measurement along direction of motion, means along x-axis, in one inertial frame is directly proportional to measurement in other inertial frame. So instead of x dash equal to x minus vt, which is the case of classical mechanics, it is proportional to x minus vt. When this proportionality sign was removed, we are having this constant gamma. And if you will see equation number 1, this is the transformation equation. Why I am saying this is transformation equation? Because all the coordinates on right hand side belongs to S frame, and the coordinate on left hand side belongs to S dash. Means you have converted the coordinates, we have converted x in terms of x dash in terms of x. So coordinates of one frame, they are converted into coordinates of other inertial frame. But there is one unknown constant in equation number 1. So our objective is to find the value of that gamma. If that unknown constant is known in terms of, if that unknown constant is calculated in terms of known parameters, then you are having a complete transformation equation. So in order to find that, we will use both the postulates of special theory of relativity. First postulate, that if you are having equation number 1 for S dash, you can have a similar type of equation for frame S. So you are having this equation number 2 here. So now in 1 and 2, the only problem is the problem of that unknown constant. So in order to find that, it was assumed that when t was equal to t dash equals to 0, both the observers, they are coinciding with each other. If they are coinciding with each other, at that time a source of light is kept at the origin, and that source of light is giving us light radiations in all the possible directions. It means it is also giving light along x-axis, and if light travels x distance in time t, then x will be c into t. And according to second postulate of special theory of relativity, if c is the speed of light in frame s, then it is also c in frame s dash. So if light travels distance x dash in time t dash in frame s dash, then x dash will be ct dash. So you have x as ct and x dash as ct dash. Now what you have to do? Substitute this x ct and x dash ct in 1 and 2. Solve these two. How you will solve these two? Just by multiplying this 3 and 4, you will get the value of gamma. Gamma, now it is known, the value of gamma is known, and it is known in terms of given parameters. So substitute this value of gamma in equation number 1, you will get your transformation equation along x-axis. Then since there is no motion along y-axis, so y dash is y. Since no motion along z-axis, so z dash is z. And in order to find t dash, what you will do? You will take that second equation number 2, that is x equal to gamma x dash plus vt dash, and you have to solve this equation for t dash. So when you will solve this, you will get t dash as gamma into t minus vx upon c square. So you know what is the value of gamma. Substitute that gamma there, you will get this equation for t dash in terms of t. So these 4 equations, they are your Lorentz transformation equations. So we have derived those equations in our previous lecture, and I have also mentioned that if you want to write inverse transformation equations, then how you will write? These are the inverse equations. Clear? Now there is a very important conclusion that classical mechanics, this is a special case. Classical mechanics, or you can say this Newtonian mechanics, is a special case of relativistic mechanics. So let me write it first. Classical mechanics is a special case of relativistic mechanics. Now I have to prove that how I can say that classical mechanics is a special case of relativistic mechanics. So for this, we are taking our these Lorentz equations. What are Lorentz equations? X dash is x minus vt upon root 1 minus v square upon c square. This is your transformation equation along x-axis if the direction of motion is x-axis. And what about y-axis? Y dash is y. What about z-axis? Z dash is z. And what about your time transformation? This is t dash t into t minus vx upon c square upon under root 1 minus v square upon c square. These are your Lorentz equations in relativistic mechanics. Clear? Now I am substituting a condition here. I am taking this condition if v is very, very small with respect to c. You know this is the case of classical mechanics. If v is very, very small with respect to c, then this particular factor, it is very, very small with respect to 1. You can neglect this factor with respect to 1. It means 1 minus 0, root 1 means 1. Means in the denominator you will get 1. So what will be the value of x dash then? It is x minus vt. It means this equation approaches to this one if you will consider this condition, if v is very, very small with respect to c. Now what about your y-axis? So there is no change along y-axis. Along z-axis, no change, z dash equal to z. Now see the last time transformation term. Since v is very, very small with respect to c, so this v upon c square, in the denominator you are having higher power of c, and c is 3 into 10 raised to power 8 meter per second. Higher power means 9 into 10 raised to power 16. So this particular factor will be very, very small. So you can ignore this factor with respect to t. So in the numerator, you will get only t, and in the denominator, since b is very small with respect to c, this entire factor can be neglected with respect to 1. In denominator, you will get 1. So what you are getting? You are getting t dash is equal to t. So what are these equations? You can see here that these 4 equations, these are Galilean transformation equations, or you can say Galilean transformations, or you can say these are the equations applicable in classical mechanics, whereas these equations, they are applicable in relativistic mechanics. So what is the conclusion? This classical mechanics is a special case of relativistic mechanics, or in other words, you can say this relativistic mechanics is equally applicable when V is comparable to C as well as when V is very, very small with respect to C. So you can apply this relativistic mechanics for all these cases. Clear? I hope now this point is clear that classical mechanics is a special case of relativistic mechanics. Now I want to take one question here. Question is, prove that x square plus y square plus z square minus c square t square is invariant under Lorentz equations. You have to prove that this space-time interval, this is known as space-time interval, you have to prove that this is invariant. Give me 1 minute. Prove that this is invariant under Lorentz equations, Lorentz transformation equations. So you have to prove this, that this space-time interval is invariant under Lorentz transformation equations. Invariance means the form of this equation that is same in all inertial frames. That is the meaning of invariance. Means you have to prove that x dash square plus y dash square, I am writing this space-time interval in S dash frame, plus z dash square minus c square t dash square is equal to x square plus y square plus z square minus c square t square. So you have to prove this. If you can prove this, then you can say this space-time interval is invariant under Lorentz equations. So what we are doing, we are taking our left hand side, and then in that left hand side we will substitute the value of x dash in terms of x using Lorentz equations. Then we will substitute the value of y dash, z dash, t dash using Lorentz equations. So first we are writing those Lorentz equations if the frame S dash is moving along x-axis. You know, if frame S dash is moving along x-axis, you can write here x dash is x minus vt upon root 1 minus v square upon c square. This is your x dash. Your y dash is y. Your z dash is z. And your t dash is, what is the value of t dash? T dash is t minus vx upon c square upon root 1 minus v square upon c square. So these are Lorentz equations. Now we have to take left hand side. So I am taking left hand side, and from that left hand side we have x dash square plus y dash square plus z dash square minus c square t dash square. Just substitute the value of all these terms, x dash from here, y dash from here, z dash from here and t dash from here. So substitute all these values. X dash is x minus vt upon root 1 minus v square upon c square. So this is the value of x dash. So square of that plus y dash square means y dash is y. So I am writing here y square simply. Z dash as z. So I am writing simply z square minus c square as it is, and your t dash is t minus vx upon c square upon root of 1 minus v square upon c square. So, square of this. So, now you are having left hand side equal to this. We have substituted x dash in terms of x, y dash in terms of y, z dash in terms of z, t dash in terms of t using Lorentz equations. Now, you have to simplify it. We will simplify it by combining these two terms, and if you will combine these two and if you will simplify, then this left hand side, that left hand side will be, it is, I am combining first and last term here. So, this is x square plus v square t square minus 2vxt minus, this is your first term, and LCM, I am combining first and last, LCM is 1 minus v square upon c square. So, from first you are getting this. Now, you have to take this last term, which is minus c square t square. Next is it will be plus v square x square upon c4, and c square is there. So, you have minus v square x square upon c square, right. So, you are getting there minus v square x square upon c square, and the last term is minus 2vxt upon c square. So, this will be plus 2v minus minus plus 2vxt upon only 2vxt, c square will get, sorry, 2v c square will get cancelled. So, first and fourth is combined, and y square plus z square will remain as it is. Now, this 2vxt, that will be cancelled by this, and what you are getting? You are getting this x square term here and a term containing x square. Just combine these two. So, if you are combining these two, so what you are getting in the bracket, 1 minus v square upon c square, this is your first term. And now you are having this v square t square and minus c square t square. I am taking minus c square t square common. If you will take this one common, the remaining factor is 1 here, and the remaining factor is minus v square upon c square here, and in the denominator you are having 1 minus v square upon c square plus your y square plus z square will remain as it is. Now, what you are getting? You are getting 1 minus v square upon c square common here. So, if you will take this as common, so 1 minus v square upon c square will get cancelled, and you are getting x square plus y square plus z square minus c square t square. So, from where you have started? You have started from left hand side. This is your left hand side, and you have reached over here, x square plus y square, means we are reaching at this particular condition. So, now you can say that this space time interval is having same form, or this space time interval is invariant under Lorentz equations, right. So, this question is over. Just practice this question, you will able to solve it. So, now I am moving to next topic. So, next one is a very interesting topic, and the name of topic is length contraction, right. So, first I will try to explain the meaning of this concept, that is length contraction concept. Now, suppose you are a stationary observer, you are sitting in a rest frame, and you are at rest in that particular frame, and I am moving in a frame S dash, I am present in frame S dash, and with respect to you, that frame is moving with a constant velocity v along x-axis. Means you are at rest, but I am present in S dash frame, and S dash is moving with respect to you along x-axis. Now, in my frame, this object is kept in frame S dash. This object, let it is AB, this object is lying in frame S dash. So, now for me, if this object is present in S dash, if it is with me and I am observer O dash, then for me this object is at rest. But for you, because you are sitting in that rest frame, for you this object is also moving with the same velocity as the velocity of S dash frame. It means for me, for S dash frame, this object is at rest, but for you this object is moving, and it is moving with the same velocity as the velocity of frame. According to this concept of length contraction, according to this concept, if we are having a moving object and if the speed of that object is comparable to c, then for the stationary observer there will be a contraction in the length of object along direction of motion. I am repeating this concept again. If a stationary observer is measuring the length of this moving object, then along the direction of motion there will be a contraction in the length of this object, and that contraction is only along direction of motion, other dimensions will remain same. So if you are a stationary observer and if you are measuring the length of this object along direction of motion, then for you there will be a contraction in the length of this object along its direction of motion. So now we will try to find out that how the length will decrease for a stationary observer, how the length will change because of the motion. So the length of any object in a moving frame will appear shortened in the direction of motion or contracted. The amount of contraction can be calculated from Lorentz transformation equations. So now we are using Lorentz equations to find that length contraction. The length is maximum in the frame in which the object is at rest. So what is the meaning of this last line? Object is kept in my frame, in S dash frame. So for me this object is at rest, but for you this object is moving. It means the length of this object will be maximum in my frame, because in my frame this object is at rest. So that is the meaning of this term. And that particular length of the object, which is the maximum length, or you can say the length of the object in that frame where the object is at rest, that length is known as proper length of the object. What I am saying, the frame in which the object is at rest, or the frame in which the maximum length of the object is measured, that particular length, or in that frame the length is known as proper length. So what we are doing here, we are taking two frames here. One is fixed frame. Suppose this is your S frame and this frame is at rest. So you are stationary observer and you are sitting in this particular frame. Your position is this. You are here, so you are at rest here. Now there is another frame which is S dash frame. So this is your moving frame, S dash frame, and I am present in this frame. So I am present in this moving frame, right? And now you are taking all the observations with respect to your frame. From here you are taking all the observation. So for you this frame is moving. Clear? Now in this frame this particular object is kept here. Let this point is A and this point is B. So you are having this object AB which is kept in S dash frame. So if the object is kept in S dash frame, object is kept in my frame, I am in S dash frame. So it means for me that object is at rest. For this observer O dash, this AB is at rest. So since in S dash object is at rest, so this particular length, this is known as proper length. The length of the object in that frame where the object is at rest, that particular length is known as proper length. So that's why I am mentioning this this length as L naught. So I hope up to here everything is clear. There is a stationary observer O sitting in this fixed frame, and there is another frame, moving frame S dash, and there is an object AB kept in that particular frame. So for this particular frame, for observer O dash, this object is at rest. So that this length with respect to O dash is known as proper length. And if the coordinate of this initial, if the coordinate of this initial point is x1 dash and this coordinate is x2 dash, then this length is x2 dash minus x1 dash. That's why this equation number 1 is written. So what is equation number 1? This is your proper length, or you can say this is the length of object in that frame where the object is at rest. So in which frame object is at rest? Object is at rest in this S dash frame. Clear? Now you are taking observations from this frame S, or this observer O is taking observations. For this observer, this object is not at rest, it is moving, and it is moving with this constant velocity which is comparable to c. So if this object is moving along this particular direction with respect to this frame, and if for this observer, the first coordinate, this particular coordinate, if it is x1, and if the coordinate of second point is x2, then what is the length with respect to O? For O, this coordinate is x1, initial, the coordinate of initial point. This coordinate is x2. So the length is x2 minus x1. So this L is equal to this x2 minus x1. So you are having equation number 1, which is your proper length, and this is the length measured by S dash frame. Because in S dash frame object is at rest, and you are having that S frame, and for observer who is sitting in S frame, that object is moving. So you are also having those coordinates with respect to S frame, and you are getting L as x2 minus x1. Now we will try to correlate L with L naught, and from there you will get an expression that whether there is any change in the length because of motion, or length will remain unaffected. That we are going to find out here. So in order to correlate these two, we have to apply Lorentz equations, and you can correlate x2 dash with x2 and x1 dash with x1. So according to Lorentz equations, just refer your Lorentz equations. X2 dash will be x2 minus vt upon root 1 minus v square upon c square, and x1 dash will be x minus vt upon root 1 minus v square upon c square. Just take this value and just take the value of x1 dash and substitute in equation number 1. You have to take x2 dash and x1 dash from Lorentz equations, and you have to substitute in that equation number 1. So after substitution, you are getting here that root 1 minus v square upon c square, that is common factor, and here you are getting x2 minus vt minus x1 plus vt. So what finally you are getting from here? You are getting x2 minus x1 upon root 1 minus v square upon c square. And what is your x2 minus x1 from equation number 2? x2 minus x1 from 2, it is L. So substitute the value of x2 minus x1 as L. So from here, what is L? L is equal to L naught into root 1 minus v square upon c square. So this is famous expression for length contraction. So how the length is contracting, we will interpret with the help of this equation. So this is your length contraction term. Now see here, this factor root 1 minus v square upon c square, just concentrate on it. This v is that can be comparable to c. If v is comparable to c but not exactly equal to c, v is comparable to c, then this factor will going to give you certain value. If this will give you certain value, then this entire factor root 1 minus v square upon c square, that is always less than 1. I can explain it with the help of a simple example. Let the value of this root 1 minus v square upon c square, since it is always less than 1, I am taking this as 0.9. let it is 0.9 and let the length, proper length is 10 meters. So if L naught is 10 meters and this root 1 minus v square upon c square, since it is always less than 1, I am taking it as 0.9. So what you will get L? That will be 10 into 0.9. It means L will be 9 meter in that particular case. Means the length of object when it was at rest, it was equal to 10 meter. But when it is moving, then for a stationary observer, there is a contraction in the length and that length is 9 meters. So if V is comparable to C, L is always less than L naught. So that formula itself is an explanation that whenever an object is moving with the velocity v which is comparable to c, then with respect to the stationary observer along the direction of motion there will be a contraction, and contraction will take place according to this formula. So length get contracted along direction of motion by this factor of root 1 minus v square upon c square. So now we are taking a special case here. Suppose v is very small with respect to c. So if v is very small with respect to c, what you are getting? This factor is having a very small value with respect to 1. So your L is equal to L naught. So if this is the case, then this is approximately 1 and L is L naught, means no change in length. And you also know, according to classical mechanics, everything is absolute, means no parameter is affected by the motion. So you can also see here, length is not affected by the motion, but that is under a particular condition, under this condition, that when the speed is very small with respect to c, means when you are dealing with classical mechanics, length is absolute, that is not affected by motion. It is always having same value as the length of object when it is at rest. But if you will take case number 2, means when v is comparable to c, when v is comparable to c, we know L is always less than L naught. And you can also take the extreme case, v equals to c. If this v is equal to c, then this factor is going to give you value 0. So L is equal to L naught. So the meaning of this is, if a particular object is moving with speed of light, then for stationary observer that will appear, this one is 0 because v is equal to c, so this is 0. It means when an object is traveling with speed of light, then it will appear as a point object. So this is your length contraction. So what I had told you in length contraction, for a stationary observer, if an object is moving and if it is moving with speed of with a very high speed which is comparable to c, then along the direction of motion there will be a contraction in the length of object, but other dimensions will remain unaffected. This change will take place only along x-axis. So this is your length contraction. So now I am going to solve a simple question here, and after that we will sum up this lecture. So what I am taking, so I am taking a meter rod. Suppose you have a meter rod, and if you have a meter rod, then I can write that the length of the rod is 1 meter because that is a meter rod. So you have a meter rod, and for a stationary observer, if that meter rod is moving along x-axis with 0.8 c, means for a stationary observer, if that object is traveling with 0.8 c, then you have to tell me what will be the length of that meter rod for that stationary observer along direction of motion. So you know, for the stationary observer, according to the length contraction concept, length will be L naught into root 1 minus v square upon c square. So since the length of the object when it is at rest is 1 meter, so this is 1 meter into root of 1 minus 0.8 c upon c square. You are getting here this 0.8 c, 0.64 c square will get cancelled, 1 minus 0.64, 0.36 under root. So you are getting here 1 meter into root 0.36. So out of this under root you will get 0.6 value. So 1 meter into 0.6, so you are getting 0.6 meter, or simply you can say 60 centimeter. So the 60 centimeter here. So if you have a meter rod with the, give me 1 minute. If you have a meter rod with length 100 centimeter or 1 meter when it is at rest, then if it is moving with this 0.8 c, then for a stationary observer, length of the object will be 60 centimeter. So here you can see that how the length will contract when the object is moving with a very high speed, which is comparable to c. So this is your concept of length contraction. Now try to solve the numerical problems based upon length contraction. We will take some more problems related to length contraction concept in our next lectures. So thank you so much for today. Thank you.